Well, hello everybody. We continue our discussions on homogeneous open systems that we had started in the last class. If you see in the last class, we had derived these four equations relating the thermodynamic potentials with their respective parameters for under different conditions of coupling between the system and the surroundings, and we had defined a new term which we found for pure substances. It is nothing but the molar Gibbs free energy, and it was defined in this particular form. Now, we would like to extend the discussions that we had yesterday slightly further, and we would like to discuss certain other aspects of homogeneous open systems. Now, since as I have already mentioned, and you also know that the temperature pressure conditions are keeping constant temperature and pressure, it's the most common thing that we encounter in practice. So, therefore, we are going to deal primarily with the equation which relates the Gibbs free energy with the other things. Now, for the time being, let me write it down. For the time being, I would like to deal with the simplest type of homogeneous open systems. What is it? It comprises of, say, one component. It's a single component system which exists in two phases. And let me tell you, this is the most common type of phase transition that we encounter, and the phase transitions are usually of the form solid to liquid, or maybe liquid to vapor, or maybe solid to vapor, and so on. These are the most common transitions that we encounter. There can also be some other types of transitions, for example, an alloy of say a lead and tin which forms a solder. That can also, here also we can have a similar type of phase transition. So, for the time being, what we do, we concentrate on one component two phase systems, and we consider the simplest type of open systems that we can think of. Once we are conversant, we are quite familiar with this, then we go for heterogeneous closed systems, or in other words, we go for a system where a large number of homogeneous open systems, it constitutes a heterogeneous closed system. Now, let us see, in this particular case, we can write down dg as del g del t at constant p n dt plus del g del p. I have written it down several times, yes, in the last class, plus del g del n1, where I would like to remind you that n1 is the number of moles of phase 1, say, n2 is the moles of component. It should be of component in phase 1, and this is moles of component in phase 2. So, this is del g del n1 under constant Tp dn1 plus del g del n2 constant Tp dn2, right. Now, at constant temperature pressure conditions, because usually we know that these types of phase transitions, they occur under constant temperature pressure conditions. So, under these conditions, what do we get? We get del g del n1 Tp dn1 plus del g del n2 Tp dn2. This should be equal to 0. Now, in the beginning, I have told you that we are dealing with a single component in two phases, and we assume that while, for example, suppose say it is a liquid vapor mixture, right, kept in a piston cylinder arrangement where the pressure is kept constant, the temperature is kept constant. We have got a liquid here, we have got a vapor here. Now, if we consider the liquid only to be a system, then it is an open system, because there is mass and energy interaction between the liquid and vapor phase. If we consider the vapor to be the system, then again it is an open system. But when we consider the liquid vapor combination to be a system, then it is a closed system. Now what do we have here? We have say N1 moles here, we have N2 moles here, and we know that since the composite system is a closed system, so N1 plus N2 equals to N, this should be something constant, or in other words what I mean to say is dN1 plus dN2 equals to dN should be equal to 0, which automatically implies that dN1 should be equal to minus dN2. So therefore, if you substitute this in this particular equation, then what do we get? We get in this particular equation, then in that condition we get del G del N1 T P N2 minus del G del N2 T P N1 into dN1 is equal to 0. What does this imply? Since we know that dN1 is not equal to 0, so it automatically implies del G del N1 at T P N2 must be equal to del G del N2 at T P N2. From yesterday we already know what is this. It is in fact it is already written here. This is nothing but mu. So therefore, from here we can write this down as d mu 1, or rather sorry mu 1 is equal to mu 2 under this condition. So therefore, if suppose transfer occurs under a condition such that mu 1 is not equal to mu 2, then in that case there is going to be mass transfer till the time when mu 1 becomes equal to mu 2. And in the process of this mass transfer, what do we find? We find that the system with the larger chemical potential shrinks, and the system with the smaller chemical potential, it increases in size till the chemical potential of both the open systems, say the liquid and the vapor in this under this condition, they become equal. Moment they become equal, we find that there is no other further interaction between the two systems, they are under equilibrium condition. So to summarize, if mu 1 is greater than mu 2, we know that dN1 is negative and the mass transfer occurs from phase 1 to phase 2, and vice versa. If dN2 is positive, then the mass transfer occurs from 2 to 1. So just the way I'll repeat, phase with the larger chemical potential shrinks and phase with the smaller chemical potential it grows till equilibrium is reached, or in other words till mu 1 becomes equal to mu 2. Now this particular equation we can extend it further to find certain other characteristics of the transition boundaries. How? All of us know that what is d mu equals to? D mu, it is nothing but equal to dg, and we already know what is dg equals to, again referring to this particular equation, since dg has been written in terms of molar quantities. So therefore this equation with the different molar quantities. So therefore this becomes minus s dt plus v dp, right. So d mu 1 it should be equal to minus s1 dt plus v1 dp. In the same way, d mu 2, this should be minus s2 dt plus v2 dp. Now what do we know? We know that d mu 1 should be equal to d mu 2. So therefore, for the two phases this should be equal to this, and from there what do we get? From there we get the famous Clapeyron equation, which can be derived as dp dt equals to s1 minus s2 by v1 minus v2. In other words, it is delta s by delta v, which is nothing but the entropy of transition, the ratio of the entropy of transition with the volume change of this. We get this as So therefore this gives us the Clapeyron's equation, you can see, where we find that the slope of the pressure versus volume curve, it is obtained from the slope of the pressure versus temperature curve, it is obtained from the entropy of transition divided by the volume change on transition. So, therefore, from this we find that the slope of the PT curves, if we observe the slope of the PT curves which I had shown in the last class, if you recollect, the slope of the PT curves can be obtained from that particular equation. The equation which we say it is commonly known as the Clapeyron equation. So, from this Clapeyron equation, what are the things that we get? First thing is, suppose we apply it, there are number of things. First thing is, this can be applicable to any phase equilibrium problem, any phase equilibrium of any particular substance, provided it is a pure substance, we can apply it. And if you observe, the important part is we find that we can use the thermodynamic data, the data on delta S, delta V, to predict the appearance of the phase diagrams and their forms. So, therefore, what I mean is we can predict the slopes of these PT curves for the different phases, and we can do we can also predict which graph is going to be steeper, which is going to be less steep, and we can do all these things using the thermodynamic data. Let us see what this particular equation reduces to. For example, if we consider the solid liquid boundary. When we consider the solid liquid boundary, what is delta S? Delta S is nothing but delta S fusion, which is nothing but delta H fusion by the melting point of the solid. So, from there what do we get? We get dP dt is nothing but equal to delta H fusion by T delta V fusion, right. Now, usually what we find, usually this delta V fusion, it is nothing but V liquid minus V solid. For most of the substances, this is positive, and therefore, it is quite evident if you observe here, this particular the slope of this particular curve, it is we see that it is more or less positive. Now, very interestingly, if you observe water, then in that case we know that delta V for water, that is going to be negative. Why? Because yesterday also we discussed, and you already know that the water, it contracts on liquefaction. So, therefore, if you observe the curve for water, what you find that there is a slight negative slope, and that arises because of the negative value of delta V fusion. We also see that in this particular case, delta V fusion is usually much smaller, and that explains for the very steep curve, the solid liquid transition curve, for both the cases that I have depicted here, and also for several other cases that you can see, or you can take up in different textbooks. So, therefore, the conclusion is that for the solid liquid boundary, we find that the slope is usually positive, except some examples like water, antimony, bismuth, and the other thing is slope is usually very steep. And so therefore, from here we can easily integrate this equation as well, and on integrating this equation, say from a pressure P1 to P2, and assuming that delta H fusion and delta V fusion, they are more or less constant with pressure, we can get an expression like the final pressure can be obtained as the initial pressure plus delta V fusion ln T2 by T1. So, in this particular equation, if we know the total number of parameters are 1, 2, 3, 4, 5, 6. Out of this, if we know 5 of the parameters, we can find out the sixth one. Well, this was for the solid liquid boundary. Now, let us apply the same equation to the liquid vapor boundary as well. So, if we apply it to the liquid vapor boundary, starting from the same Clausius-Clapeyron equation, we know dP dt, this is equal to delta S by delta V. So, therefore, when it is liquid vapor, then this is going to be delta S vaporization and the delta V vaporization. So, this is nothing but delta H vaporization by T, the boiling point temperature, into V vapor minus V liquid. Now, in this particular case, usually unlike the solid liquid transition, we know that usually the V vapor is much greater as compared to the V liquid, and we also know that for low to moderate pressures, this can be equal to, this obeys the ideal gas equation. So, from here we can write this down as dP dt is nothing but equal to delta H vaporization by RT square by P, or we can also rearrange it to write to denote dln P dt is nothing but equal to delta H vaporization by RT square, and this particular equation is known as, it is a very famous equation, it has got a lot of applicabilities, and this equation is known as the Clausius-Clapeyron equation. On integrating this equation, what do we get? On integrating this equation, we get ln P2 by P1, this is equal to delta H vaporization by R into 1 by T1 minus 1 by T2. So, therefore, what does this imply? This implies so therefore, I have just written down the equations which we were discussing. For solid liquid transition, this is the equation. For liquid vapor transition, the Clausius-Clapeyron equation has been derived, and from this equation it is quite evident that ln P versus 1 by T should be a straight line. And here I have depicted for a large number of liquids the log P saturated versus the 1 by T, and we find the linear nature of the curve for all the substances, despite the large number of assumptions which are inherent in this particular derivation. We will discuss the assumptions shortly after we deal with the solid vapor boundary. Now, in the solid vapor boundary also it is almost the same thing, and the only thing that we do is we replace delta H vaporization with delta H sublimation, as a result of which the equation which we obtain in this particular case is ln P, or else I will write the better form, dP dt, it is nothing but delta H sublimation by RT square by P. And keeping in mind that delta H sublimation is nothing but delta H vaporization plus delta H fusion, this automatically explains that if you observe the PT curve, you will see that the solid vapor transition line, it is much steeper as compared to the liquid vapor transition line, and this can be explained from the fact that it arises since delta H sublimation is involved in the solid vapor the PT curve of the solid vapor transition curve, and delta H sublimation is much greater as compared to delta H vaporization. So, therefore, from here we find that generally for transition from the condensed phase to the vapor phase, we find that the equation can more or less be written in the form as log P or log 10 P, it is something of A minus B by T. The equation is something of this form, and from this log P or ln P, in whatever way you wish, you can write it down. And you see the utility of this particular equation. The utility of this particular equation, or even the equation written in this form, is, first thing, we can predict the P versus T curve from thermodynamic data on latent heat of vaporization. So, therefore, from here the first thing that we can find out is that how vapor pressure varies with temperature. This is the first thing that we can find. The other thing that we can find is how boiling temperature or boiling point varies with pressure. And the other interesting thing which we can find is we can find out delta H vaporization from PT data. This is the other important thing. We can find data on delta H vaporization as well as delta H sublimation, both of them, and from the data. From here, if we try to find out delta H vaporization, it is nothing but equal to RT square by P dP dt. Similarly, delta H sublimation, it is nothing but equals to, we can write it down in this particular form. So, therefore, we find that from these equations which we have derived from the basic equation of homogeneous open systems, the simplest type comprising of single component and two phases, what do we find? We find that we are in a position to predict the slope of the PT curve here, and also if we know the slope, we can predict the heats or the enthalpies involved in the transition criteria. Now, we need to remember, despite the success of the Clausius-Clapeyron equation, it has got a large number of assumptions. Now, what are the assumptions? The first and the most serious assumption is, for all these integrations that we have done here, I have assumed a basic thing that delta H vaporization is constant. Only under that condition I have come from this step to this step, and this is the most drastic assumption, because if you observe the PT curve, you are the PV curves, we can very well observe for the liquid vapor zone. We will be discussing this in the next class, and then it will be clear to you how the most drastic assumption is regarding assuming the constancy of delta H vaporization, the latent heat of vaporization. So, we continue with this discussion in the next class.